Now let us start numericals in chemical kinetics. Generally, majority of the questions in chemical kinetics, the numericals are based on zero order, first order, and second order. Not much questions actually comes from second order, but zero order and first order reactions are very important. Plenty of problems are there where you need to oscillate your practice in zero order and first order. So in that scenario, two important relationships you have to remember in terms of zero order reaction. In zero order reaction, always T75% is equal to 3 by 2 into T50%. T50% is nothing but half-life of zero order, and T75% means 3/4 of the reactant. 3/4 of the reactant has been completed into product. So based on that, T75% is equal to 3 by 2 of half-life of the zero order. Then 100% of time of 100% of the reaction is equal to 2 times the half-life of the zero order reaction. So this, in the simplified version, I have also given you the simplification of how we get the relationship between T100% and half-life of the zero order reaction, and T75% into T75% is equal to 3 by 2 times the half-life of the zero order reaction also we are noticing here. So these two formulas are very, very important when we are trying to solve some problems in this chapter, that is chemical kinetics. Similarly, if you go for first order reaction, half-life is equal to 3 by 10 into T of 90%. T of 99% is equal to 2 times that of the T of 90%. 99.99% is equal to 4 times the time of 90%, so on and so forth. For example, in first order, if you want to prove, in first order, let us prove this case. Suppose, for example, if I am taking this particular case, T50% is equal to 3 by 10 into T of 90%, already I gave you the relationship. In the zero order, already we have derived using the expression. So now suppose in the first order, if you want to prove that T50% is equal to 3 by 10 times of the T90%, then what we can do is T50% of first order, I mean half-life of the first order, is given by the equation, that is T half is equal to 0.693 by K. Keep this as first equation. Then again T of 90% means T is equal to 2.303 by K into log of, initially let us take A by A minus X. If it is A by A minus X or C naught divided by C naught minus X, whatever, initially the initial concentration of the reactant is 100, because already it is 90%. If it is 90%, T 90%, what do you mean by that? That means 90% of the reactant has been converted to product, still some 10% of the reactant is left. So if that is the case, 100 minus 90 is only 10. So if you take this, this is going to become log 10 in the 2.303 divided by K into log 10. Log 10 is 1. So therefore this is going to become T 90% is equal to, that is 2.303 by K into, that is 1, because log 10 is 1 here. Log 10 is going to become 1. In the meantime, let this be equation 2, but equation 1, again equation 1, from equation 1, if T half is equal to 0.693 by K, I am going to write this value, I am going to expand. So dear students, so if I expand this T half, which is T50%, this is nothing but 2.303 into log 2 divided by K. So this expanded version of 0.693 by K, if you take, then let this be, this is the expanded form. So take both the cases now, that is equation 2 divided by equation 1. If I take in equation 2, we have, that is equation 2 is nothing but, if you are taking equation 2, this is nothing but this is T90, this is nothing but T90 means it is nothing but 2.303 by K, and equation 1 is 2.303 into log 2 is 0.3010 divided by K. So K gets cancelled, 2.303 also gets cancelled. This is nothing but 2.303 is for T90%, 2.303 is for T90%, and divided by this is for T 50%. So this is going to be, this expression is going to be, that is T 90% divided by T 50% is equal to, T 50% is equal to, this is going to be, it is in the denominator, so this is going to be 0.3, approximately I am taking 0.3010 as 0.3. So 0.3 means 1 by 0.3. So T 90% is equal to, T 90% is equal to 10 by 3 of T of 50%. So this is how we have derived the expression. So every time if you want to derive the expression like this, it may be a problem for us, to derive every time, each and every case. So that could be a problem. So we have to be little bit careful. So my dear students, if you go to the numericals in chemical kinetics, this is the first numerical which we are trying to handle. If you look into this problem, he says that a reactant A is getting converted to B and its rate constant is given by Ka, which is equal to 10 to the power of 15 into exponential form of minus 2000 divided by T. T is the temperature. Again, the next reaction follows where the reactant C is the reactant and D is the product. So reactant C is getting converted to product, in which the rate constant Kc is given by Kc is equal to 10 to the power of 14 into exponential form of minus 1000 by temperature. So he is just asking us, suppose if you are assuming both the rate constants of both the reactions, the reaction A and A gives rise to B and C gives rise to D, the rate constants Ka and Kc for both the reactions, if they are equal, then at what temperature both the rate constants Ka will become equal to Kc. So then let us solve this problem. So assuming, let us begin the problem like this. Assuming rate constant Ka is equal to Kc for both the equations, for both the reactions, A gives rise to B and C gives rise to D, then we can just substitute both the values of Ka and Kc. If rate constants Ka is equal to Kc, for Ka we have the expression 10 to the power of 15 into exponential form of minus 2000 divided by temperature is equal to 10 to the power of 14 of into exponential form of minus 1000 by temperature. So this is going to become, if you bring the 10 to the power of 14 to the LHS side, this is going to become 10 to the power of 15 divided by 10 to the power of 14, and you take the exponential form of minus 2000 divided by temperature to RHS side, then this is going to become exponential form of minus 1000 by T divided by exponential form of minus 2000 divided by temperature. So if that is the case, this is going to become 10 to the power of 1 or simply 10, which is equal to exponential form of plus 1000 divided by T temperature. So that means what is happening here? You bring the exponential form to the LHS side, it is going to become ln of 10, because when the exponential form, this is log base C, when you bring to the LHS side it becomes ln. Ln is nothing but, that is when you bring the exponential form to the LHS side, it is ln, that is 1000 plus of 1000 divided by temperature. 1 ln is equal to 2.303 of log multiplied with 10 is equal to 1000 divided by T. But log 10 is 1. So if log 10 is 1, then this is going to be, that is 2.303 into 1 is equal to 1000 by temperature. So finally temperature is equal to 1000 divided by, bring the 2.303 to the RHS side again, 2.303, temperature is expressed in Kelvin. So therefore finally we have to understand that if the rate constant Ka is equal to Kc for both these equations, A gives rise to B and A gives rise to B and C gives rise to D, if both the equations the rate constants are equal, then at this particular temperature, that is 1000 by 2.303 Kelvin, you can expect that rate constants of Ka is equal to Kc. So therefore search for the option that is 1000 by 2.303 Kelvin, means it is fourth option is correct. So this is how we need to approach towards the problems. So my dear students, look at this question, the next numerical in chemical kinetics. Look at this problem which is given to us. The decomposition of ozone proceeds as O3, because you know very well that ozone is highly unstable oxide of oxygen. I mean allotropic nature of the oxygen is O3 and O2. O2 is paramagnetic in nature and O3 is diamagnetic, and if it is diamagnetic and it is highly unstable and it has a tendency to immediately decompose itself releasing nascent oxygen, and this nascent oxygen has the oxidizing property. So, if that is the case, what exactly we need to understand here is, in the first reaction, when ozone is trying to decompose to give 1 mole of oxygen and 1 nascent oxygen, the reaction is a fast reaction, and in the next reaction, of course, in the next reaction is followed by the slow reaction. This nascent oxygen which is released by the ozone, in turn 1 mole of O2 is reacting with the nascent oxygen to give 2 moles of oxygen. Generally, what we are going to do is, generally the slowest reaction, the slowest step is going to become the rate determining step, and if it is rate determining step, just we try to depend only on the slowest step in deciding the order of reaction. And earlier also I told you, the order of reaction never depends upon the stoichiometry of the equation, but it depends upon the reaction mechanism, and that too the slowest step. From the slowest step we can decide the order of reaction. But then here interestingly, first he has given the reaction, reversible reaction, and the second reaction is an irreversible reaction. So first we will work out the irreversible reaction, then we will go for reversible reaction, then we will try to predict the overall order, and then let us see what is happening, whether we could match any one of the option which is given to us. So how do you approach this problem? So take the second step, which is the slowest step. Take the slowest step and write the rate equation for that slowest step. When you are writing the rate equation for the slowest step, let this be equation 1 and let this be equation 2. From equation 2, that is nascent oxygen plus 1 mole of O2, both of them depends on the rate. So when you are writing the rate equation, rate is directly proportional to, that is concentration of O2 into concentration of nascent oxygen. Remove the proportionality, you are going to get a constant. Rate of reaction is equal to, small r is the rate of reaction, is equal to rate constant, concentration of O2 into concentration of nascent oxygen. Keep this equation as standby. From the second equation we got one more new equation, that is equation 3. Keep it like that. Now you take the second take the equation 1. From equation 1 we have, because it is a reversible reaction, be careful, if it is a reversible reaction then we can apply the equilibrium constant for this reversible reaction. When you are applying the equilibrium constant, yes, that reaction we can directly change it to, that is equilibrium constant Kc is equal to concentration of O2 into concentration of nascent oxygen divided by concentration of O3. Bring out the nascent oxygen from this equation, from this relationship you try to solve the expression for nascent oxygen. From this expression of equilibrium constant, bring out the nascent oxygen. Nascent oxygen is equal to equilibrium constant into concentration of the ozone divided by concentration of O2. Let this be, that is equation 4, and substitute equation 4 in equation 3. Substitute equation 4 in equation 3. R is equal to K into concentration of O2 into, that is nascent oxygen, means you please try to take this in the place of nascent oxygen, you try to substitute this expression equilibrium constant. Nascent oxygen is equal to equilibrium constant into concentration of the ozone divided by concentration of that is oxygen. So substitute in the place of nascent oxygen here this expression, that is Kc into concentration of O3 divided by concentration of O2. So my dear students, if you look at this step, if you are looking at the equation 3, rate of reaction is equal to rate constant into concentration of O3 into nascent oxygen. This is equation 3. As already I told you, substitute the equation 4 which we got, nascent oxygen is equal to equilibrium constant into concentration of O3 divided by concentration of O2. So substituting the equation 4 in equation 3, so equation 4 in equation 3 is rate of reaction is equal to the rate constant into concentration of ozone into concentration of nascent oxygen. So from the equilibrium constant we have already worked out the concentration of nascent oxygen, which is equal to equilibrium constant into concentration of O3 divided by concentration of O2. So therefore substituting this expression Substituting this expression in this nascent oxygen, right now it is very clear that rate of reaction is equal to rate constant into concentration of O3 into equilibrium constant into concentration of O3 divided by concentration of O2. So that means this expression, next step, I am just working out next step here. So rate of reaction is equal to concentration of O3 into concentration of O3 is going to become concentration of O3 square, concentration of O3 means concentration of ozone to the power of 2 into this Kc and K, the equilibrium constant and rate constant together is given by K dash divided by concentration of O2, since here I can write that is equilibrium constant into rate constant is equal to K dash. That is justified there, and finally now rate of reaction is equal to, that is K dash into concentration of O3 to the power of 2 into concentration of O2 to the power of minus 1. It is in the denominator, we are bringing it to the numerator. When you are bringing it to the numerator, we are going to get finally rate of reaction is equal to rate constant into concentration of O3 to the power of 2 into concentration of O2 to the power of minus 1. So therefore, just let us see whether we could match any of the options which is given to us. This is first option, second option, third option and fourth option. Might be not fourth option, sorry, we can go with the second option is correct, because rate of reaction is equal to rate constant into concentration of O3 to the power of 2 into concentration of O2 to the power of minus 1, which is matching the final answer which we got. So this is how we need to solve this problem. It's a very important model in calculating the overall order of a reaction when two different equations are given to us. One is fast reaction and the other one is slow reaction. So my dear students, so let us continue the next numericals, next part of the numericals. Look at the numerical here, the given numerical. The problem is based on, if you go to the problem number 3, numerical 3, the problem is based on zero order reaction. As already I told you earlier also, whenever you have a relationship in the given order of reaction between T 50% to T 75% or to T 87.5% to T 99.9% or 10% to 90% or whatever, different kind of percentage compositions are there, it is always better for you to generalize the formulas and keep that formulas in your mind. And we have already derived this expression in the earlier session. We have also derived this expression saying that for zero order reaction, T 75% of the zero order reaction is equal to 3/2 of the T half life of the zero order reaction, and also T 100% of the zero order reaction is equal to 2 times the half life of the zero order reaction. Already we have derived it. So what the problem says is, if the half life for zero order reaction, T half is half life, T half means 50%, T 50% or T half of zero order reaction is 250 seconds, then what is the time taken for the 75% of the completion for a zero order reaction in a given reaction, and what is the time taken for the completion of the reactants to products if the time is 100% of the completion of the reaction respectively in seconds. So in case when you can just solve this with respect to T 75% and T 100%, you can straight away use these two formulas. That is, in first case with respect to T 75%, with respect to T 75% for zero order reaction, with respect to T 75% for zero order reaction, you already know that it is 3/2 of T half or T 50%. This is for zero order reaction. So directly what I am doing here is 3/2 into 50% for half life for zero order reaction is already given in the problem, that is 250. So this is going to become 3 into 125. So 2 1s are, 2 125s are. So this is going to become 3 into 125, 375 seconds. This is first part of the problem. Now go to the second part. In the second part, that is with respect to that is T 100% of the zero order is equal to 100% of the zero order is equal to 2 times of half life of the zero order. Already T half of the zero order reaction is given, which is 250 seconds. So therefore it is going to become doubled. T 50% from T 50%, if it is T 100%, the given time taken will be doubled from 50. If 50% of the zero order is 250 seconds for the reaction to get completed, then for T 100% is double the T half. So obviously this is 2 times of 250 seconds, which is going to become 2 into 250, which is equal to 500 seconds is the answer. So therefore we got two different values. One is T 75% for the zero order and T 100% for the zero order. comes to 375 seconds as well as 500 seconds. Search for the correct option. The correct option would be obviously 375. So 375 means you go to the second option. In the second option, for T75% of the zero order, it is 375 times 375 seconds, and for T100% it is 500 seconds is the answer. So second option is definitely correct. Now look at this question. It is simply based on the Arrhenius equation. In the Arrhenius equation, that is, this problem is actually based on the Arrhenius equation, that is log K is equal to log A of minus EA by 2.303 of R into 1 by D is the actual expression we are supposed to use it, the hint for this question. So that means which factor should actually register a minimum value if the temperature increases for any reaction repeatedly. In the earlier sessions I told you that for every 10 degrees centigrade the rate of reaction is going to get doubled or tripled. That means whenever there is an increase in the temperature for a given reaction, chemical equation which is getting commenced, every time the temperature is increasing by a factor of 10 degrees centigrade, the rate of reaction is going to get doubled or tripled. That means when the temperature increases, the rate of reaction also increases. When temperature increases, rate of reaction increases, then automatically the activation energy of that particular reaction during the increase of temperature has to decrease. So actually it is the activation energy is the term in the Arrhenius equation which has to register itself with its decrease of its value. That means if the activation energy decreases, rate of reaction gets doubled. When the rate of reaction gets doubled, then automatically for every 10 degrees centigrade also the rate of reaction continuously gets doubled. So that means if the temperature increases, rate of reaction increases. If the rate of reaction increases, activation energy has to decrease. So it is the activation energy term which has to always register a decrease in its value when there is increase in the rate of reaction. So this expression, if you want, we can also write this as, that is K is equal to A into exponential form of minus EA by RT. So here you can easily see that the activation energy is having a negative value. The negative value here we mean, that means when the rate constant is increasing, the activation energy has to decrease. But if you look at the ratio, the temperature is dropping from 310 Kelvin to 300 Kelvin. That means from 310, this is 310, from 310 Kelvin to 300 Kelvin means there is a decrease in temperature. Overall you are finding that temperature is decreasing. When temperature is decreasing, rate also decreases. Rate or rate constant of the reaction also decreases. When the temperature decreases, rate constant decreases, then automatically activation energy is the term which registers increase in its value. Activation energy registers increase in its value. So that means among these four equations, because the temperature is dropping from 310 Kelvin to 300 Kelvin, then you have to find that in whichever case the activation energy is highest, in that case, in that particular transformation, you find that maximum amount of activation energy is generated. So if you look into the fourth option, in the first option 50, then the last option it is, second option it is 40, least activation energy. In the fourth option, highest activation energy. That means in this combination, when there is decrease in the the temperature from 310 Kelvin to 300 Kelvin, the maximum amount of increase in the activation energy also takes place. So therefore we can have an easy guess that the fourth option could register the maximum amount of increase in the activation energy, because there is a decrease in temperature from 310 Kelvin to 300 Kelvin. So my dear students, if you will go to the next part of the numerical in chemical kinetics, look at this diagram. This problem is based on the energy level diagram. From the energy level diagram, we are supposed to calculate the activation energy changes in the forward reaction or backward reaction, forward activation energy or backward activation energy. We are trying to use that concept and we are trying to solve this question. If you look into the energy level diagram, something should strike you. What is that it is striking you? It is a very clear case of exothermic reaction coordinate. This diagram which you are able to see is a clear case of exothermic reaction coordinate, because suppose if I take this part as R, that means this is reactant. F stands for reactant and P stands for product. P stands for product. So that means from the diagram it is very clear that the energy of the reactant molecules are greater than the energy of the product molecule. Suppose if I scale the potential energy values for the molecules in kilojoules per mole, this is 20, this is 40 and this is 60, this is 80 and this is 100, say for example, kilojoules per mole. It's a very clear representation that energy of the reactants are more than that of the energy of the products. So I will extend this From the reactants, if I extend a bit farther, I can take that this is energy of the reactants and this is going to be energy of the products. Okay, fine, that is not a problem. Now here, now this is threshold energy, the maximum height at which the curve is obtained gives us the activated complex, and from there, because of the effective collisions or fruitful collisions, all the reactant molecules gets converted to product molecules after acquiring sufficient amount of activation energy. So that means this Y stands for activation energy of the reactants, and here, so what is the activation energy of the products means, I can just extend one more here. This is the activation energy, this is the activation energy of the products. This we do not know. Let us imagine that we do not know what is the activation energy of the products, but the energy difference between the reactant molecules and the product molecules in the curve of this energy level diagram will give us the enthalpy change. So here delta H is equal to X, enthalpy change is equal to X. So you know pretty well that you can apply this formula directly from this observation, from the diagram itself we can calculate the correct relationship between enthalpy change between the reactants and products, activation energy of the reactants and activation energy of the products. If you take the relationship, enthalpy change is equal to activation energy of, because you are finding that the activation energy of the products are greater than the activation energy of the reactants. So I will take activation energy of the products minus activation energy of the reactants. So because anyhow he is asking reverse reaction for the following observed energy level diagram is, reverse reaction means obviously activation energy of the product will give you the backward reaction and the activation energy of the reactant will give you the forward reaction. So therefore here enthalpy change is X and activation energy of the products are giving the backward reaction or reverse reaction activation energy, it is giving enthalpy of the reactant is Y. So therefore from this you can easily calculate activation energy of the product, that is reverse reaction, is equal to X plus Y. So therefore X plus Y is the activation energy of the products, and this activation energy of the products is also giving the reverse reaction. So therefore activation energy of the reverse reaction is equal to X plus Y. So therefore you can take the third option is the correct option. Now look at this. This is something interesting. Again, this problem is based on the Arrhenius equation, temperature dependence on the rate of reaction, rate equation, the temperature dependence of the dependence on the rate of reaction. Arrhenius equation is given by, that is, look at this formula, rate constant is equal to, I am just taking out that formula, rate constant is equal to Arrhenius constant into exponential form of minus 40,000 divided by temperature. The best thing what we can do here is we can just convert this into ln form. Ln of k is equal to ln of a of minus 40,000 divided by temperature. Convert this ln into 2.303 of log, because 1 ln is equal to 2.303 of log. So 2.303 of log k is equal to 2.303 of log a minus 40,000 divided by temperature, dividing LHS and RHS with the, dividing the LHS and RHS with the, that is 2.303, we are going to get here, that is log k is equal to log a minus 40,000 divided by 2.303 into temperature. But actually if you equate this expression with the original Arrhenius equation for the temperature dependence, so we can just, this is the given expression, that means we are trying to convert the given data into the Arrhenius expression. So log k is equal to log a minus 40,000 divided by 2.303 into temperature means original equation also we know. What is original equation? Log k is equal to log a minus Ea by 2.303 of r into 1 by t. This is the original expression we know. This is the Arrhenius equation. Original Arrhenius equation. This is the original Arrhenius equation. So take this term minus Ea, take this minus Ea by, that is minus of activation energy divided by 2.303 into R into 1 by T. T is the temperature. So take this and equate with minus 40,000. So on equating, I'll take it like this, on equating minus EA by 2.303 of R is equal to, this is minus 40,000 divided by 2.303 of T. T is the temperature. So, minus of minus gets cancelled, 2.303, 2.303 also gets cancelled, but because the answer is given in calories, in each option he has given the answer in calories. So, therefore, we can take the universal gas constant value as calories per mole per degree. So, therefore, I can just take this as finally T is equal to 40,000 into R, which is equal to 40,000 into R value is 2 calories per mole per degree or mole per Kelvin. So, this is going to become 80,000, which is equal to 8 into 10 to the power of 4 Kelvin. 8 into 10 to the power of 4. The activation energy, sorry, this is temperature also gets cancelled. This is minus EA by 2.303 of 1 by T. I am sorry, this is 1 by T. Okay, T also gets cancelled. Temperature also gets cancelled. This is going to become activation energy, not temperature. So, I am cancelling the temperature also. So, activation energy is equal to that is 40,000 into universal gas constant. So, 40,000 into 2 is equal to 80,000. 80,000 is nothing but 8 into 10 to the power of 4 calories is the activation energy for the given reaction. So, therefore, we can go for the third option is correct. 8 into 10 to the power of 4 calories is the activation energy present for this given expression in terms of Arrhenius equation. So, my dear students, let us see the next numerical in chemical kinetics, that is we are going to the 7th, 8th and 9th numerical. In this, let us solve the 7th case. 7th numerical, what he says is, mind you, this is first order reaction. This is a first order reaction. In the first order reaction, fraction of the total concentration of the reactant varies with time t is equal to. This is what he is asking. Until unless you work out this question properly, it is very difficult for us to guess which is the correct option. So, what I am doing here is, because he has used the word first order reaction, I will take the help of the first order reaction. So, in the 7th question, according to the first order reaction already we know the formula. First order reaction, you know the formula for first order reaction, that is T is equal to 2.303 by K of log, that is C0 by C. C0 by C is the formula for the first order reaction. So, this expression I am going to write it as K into T is equal to 2.303 of log C0 by C is the concentration. Then you can take this 2.303 of log is nothing but ln. So, Kt is equal to ln of, that is C0 divided by C. So, if I bring this ln, one ln is equal to 2.303 of log, I will bring this ln to the LHS side. So, this is going to become exponential form of plus of Kt is equal to C0 by C. But because he is asking us to calculate the fraction of the total concentration of the reactant, fraction of the total concentration of the reactant means the amount of reactant left to that of the total amount of the reactant originally present. So, that is why what I am going to do here is, if I reciprocate this step I can reciprocate it. If I reciprocate it, this is going to become exponential form of minus of Kt is equal to, that is C by C0. So, C by C0 is the exact fraction. This C by C0 on the RHS side is nothing but the fraction of the total concentration of the reactant, which is varying with time. So, therefore, here this C0 by C is the C0, that is C by C0 is the fraction of the total concentration of the reactant varying with time in the first order reaction, which is equal to exponential form of power of minus of rate constant, negative power of rate constant into, that is time, T for time, K for rate constant, exponential form of the negative power of rate constant into, that is time is equal to the remaining concentration of the reactant divided by initial total concentration, that is C by C0 is equal to exponential form of power of minus Kt. So, therefore, we can outright go for the fourth option as the correct answer. Yes, so 7th one is done. 8th question is a damn easy question, because very simple, he is saying that which of the following represents the time to complete 90% of the first order reaction, means For first hint is he has given order of reaction which is first order. Second is he himself, he says that the reaction is almost 90% completed. If the reaction is 90% completed means for the eighth one, for eighth question you can just directly take if A is the reactant giving rise to product. If A is the reactant which is giving rise to product at T is equal to 0, at T is equal to 0 you find that let the initial concentration be equal to C0 is equal to 100, no products have been formed. At T is equal to T, you find that out of 100%, 90%, he says that 90% of the products have already been completed. So that means only 10% is remaining. So if 90 moles per liter of the concentration of products have been formed means at T is equal to T, C0 minus C is going to become only 10 moles per liter is the concentration which is left out. So directly you can apply the formula, that is you can take here T is equal to 2.303 divided by K into log of initial concentration is 100, then remaining concentration at T is equal to T is only 10. So 0 gets cancelled. So T is equal to 2.303 divided by K, 2.303 divided by K into log 10 is 1. So therefore T is equal to 2.303 divided by K is the answer. So 2.303 divided by K means obviously we can go for the third option. So third option is correct. Now look at this. Amount left after completion of average half-life in the first order reaction. So here also what we can do here is we can take average half-life means I think we can take because he is using the word average half-life, I will just try to apply the half-life is equal to 0.693, that is for ninth one. Half-life is 0.693 divided by K, and T half is equal to 2.303 into log 2. 2.303 of log 2 means divided by K means that is T half is equal to this 2.303 is ln of 2 divided by that is K. Now if I am going to bring the T, if I am going to bring the ln to LHS side, this is going to be that is I can take K into T half is equal to 2, K into T half is equal to 2, then this ln of 2, and from this if you solve then you are going to get exponential form of plus of K into T half is equal to 2. Upon simplification of this expression, or you can directly take, or you can solve this directly with first order reaction also. K is equal to 2.303 by T of log A by A minus X also we can solve. Then upon solving, definitely from solving we are going to get that is A by E is the final answer for the ninth question. It's a simple simplification, you can just carry out and you will get the answer as the fourth option in the ninth numerical. So my dear students, let us continue the next part of the problem. Let us do one problem based on in kinetics. Let us do some problem based on rate of disappearance is equal to rate of appearance. If you look into the 10th problem, what you are noticing here is, let me explain the 10th problem. Just focus on the equation which is given to us. Reactant A reacts with 1 mole of reactant A, reacts with 3 moles of the reactant B to give rise to 2 moles of reactant C. So when you apply rate of disappearance is equal to rate of appearance, then what you can notice here, that is A plus A moles of gas plus 3 moles of B of gas gives rise to, that is 2 moles of C of gas. So therefore, if you write the rate equation for this, this is minus of change in concentration of A divided by change in time is equal to minus of 1 by 3, because the molar coefficients have to be reciprocated. So minus of change in concentration of B divided by change in time is equal to plus of 1 by 2 into change in concentration of C divided by change in time. Now here he already gave the rate of disappearance of reactant A is already given to us. How much it is given? Rate of disappearance of A is nothing but equal to 3 into 10 to the power of minus 3 moles per liters per minute. So what we would like to do is, because what is the value of change in concentration of B, rate of the change in B, that means the rate of disappearance of B is equated with the rate of disappearance of reactant A. Rate of disappearance of the reactant A is equated with the rate of disappearance of the same reactant B in the reactant side. So therefore, on equating, what we can do here is, on equating, this I can take it as this ratio, I will take it as minus of minus, I will just write it like this, minus of negative of rate of reactant A is equal to negative of 1/3 into rate of B. Both are in the form of rate of disappearances. So negative sign is getting cancelled. The rate of disappearance of A is given, which is equal to 3 into 10 to the power of minus 3, which is equal to 1/3 into rate of disappearance of the reactant B. Then this is going to become equal to, that is R is equal to, that is 9 into 10 to the power of minus 3, 9 into 10 to the power of minus 3, this should be 9 into 10 to the power of minus 3, not 5. So therefore, the answer will be moles per liter per minute is the answer for the 10th question. So 10th numerical. So we will go with the second option, that is 9 into 10 to the power of minus 3. Next, if you go to the 11th question, which order obeys the expression of T half is equal to 1 by Ka? So we have one generalized equation for 11th one. I would like to give you hint. If you go for 11th one hint, if you take 11th one hint, that is T half is inversely proportional to 1 by A to the power of n minus 1. So if you want to get K into A, that means this expression is going to become T half is equal to 1 by K into the rate constant comes to denominator A to the power of n minus 1. So if you want K into A, if you want to get K into A, that means we are getting 1 by K of A. 1 by K of A means what value if you are going to substitute here, it is going to become 1 by K of A. That means we have to substitute the n value, that is T half is equal to 1 by K into A to the power of 2 minus 1, which is equal to, that is 1 by Ka. That means therefore order of reaction is 2, since n value is 2. If it is n value is 2, then it obeys the equation T half is equal to 1 by rate constant into initial concentration of A. So therefore, because we want the equation to obey reciprocal of K into A, that is rate constant into initial concentration, so we can take the order 2. So therefore, third option is correct. Option 3 is correct. Now going back to the 12th question, it is a simple energy level diagram again. Energy of the forward reaction is 85 kilojoules and the energy of the backward reaction is, it's what is asking. So without drawing the energy level diagram, the generalized expression we already know. If you take the generalized expression for 12th one, taking the hint for 12th, that is generally in general enthalpy change is equal to activation energy of forward reaction minus activation energy of the backward reaction is the common formula which we are going to use without drawing the energy level diagrams in general. So directly let us apply the energy level diagram generalized formula. So enthalpy change is already, it is minus 20 kilojoules and is asking us to calculate the energy of the backward reaction. So energy of the forward reaction is already 85. So minus of activation energy of the backward. So activation energy of the backward is equal to 85, bring minus 20 to the RHS side plus 20. So this is going to become 105 kilojoules per mole. So therefore, the answer is 105 kilojoules per mole. So go to the second option. Second option is correct. My dear students, look at this problem. Based on the experimental data, we can predict the order of reaction. So what hint I would like to give for 13th question is, hint for 13th question is, first hint is the order of reaction can never be predicted by the stoichiometry of the equation. So that point you have to keep it in your mind. Order of reaction is experimental, never predicted by stoichiometry of equation. Never predicted by stoichiometry of the equation. So then what is the solution for this? Then how can we predict the order of reaction? So what we are going to do is, don't depend on the molar coefficients, whatever he has given in this equation, don't depend on them. You blindly write the rate equation. You know very well that when you are writing the rate equation, The rate always depends upon the concentration of the reactants only. So, when you write the rate equation from the observed experimental data, I am writing the rate equation as rate is directly proportional to concentration of nitric oxide to the power of m into concentration of chlorine to the power of m. If you remove the proportionality, you are going to get R is equal to K. R is nothing but rate of reaction and K is the rate constant. So, that is concentration of nitric oxide to the power of m into concentration of chlorine to the power of n. This is n here and this is n. Okay, fine. Now, if you have a close look into the data which he has given, this is rate expressed in moles per liter per second, and this is expressed in moles per liter. Concentration in moles per liter. Here also moles per liter is the concentration. This is the experimentation. So, this is the data which you need to keep it in your mind here. So, if you are observing very carefully, what you are noticing is the first two, experiment 1 and experiment 2 is correlating with the same concentration for chlorine. You can see the concentration of chlorine is same with respect to the concentration of chlorine is same with respect to 0.02 molars from the experiment 1 and experiment 2. In the experiment 2 and experiment 3, two different combinations you have to take. In the first case, you have to take the two combinations of experiment 1 and experiment 2, that is 2.4 into 10 to the power of minus 4 and 2.16 into 10 to the power of minus 3 you need to take. And in the second case, you need to take experiment 2 and experiment 3 because here the concentrations are same. So, what I am going to do is I am going to work out the first two cases, 1 and 2 I am going to work out, experiment 1 and experiment 2 I am going to work out. So, therefore, I will take it like this, that is from experiment 1, 2, their respective rates I am taking. If I am taking their respective rates, what you have to observe is 2.16 into 10 to the power of minus 3 is higher than 2.4 into 10 to the power of minus 4. So, that is why what I am going to do here is I am going to take the second experiment divided by first experiment. So, from the experiment 1 and 2, 2 divided by 1 means here you can take the rate as 2.16 into 10 to the power of minus 3 divided by 1 means 2.4 into 10 to the power of minus 4 is equal to, that is concentration of chlorine is same. So, therefore, I am going to take, if the concentration of chlorine is same and the concentration of nitric oxide is 0.03. So, I am going to take, that is 0.03 divided by 0.01 whole power of, because this is 0.03 and 0.01 is with respect to nitric oxide. So, nitric oxide we have treated it as m. So, to the power of m into concentration of chlorine if you take 0.2 and 0.2. So, therefore, I am taking 0.02 divided by 0.02 whole power of n. Because the concentrations are same for with respect to chlorine, the concentrations are same, I am going to cancel altogether the n component 0.02, and this is going to be roughly, I am going to take this value 2.16 into 10 to the power of minus 3 means this is going to be roughly upon simplification you can take this as, that is 2.16 divided by 2.14 into 10 to the power of minus 1, 10 to the power of, not 10 to the power of minus 1, sorry, this is, I think we can take it as 10 to the power of minus 3 into 10 to the power of plus 4 is equal to, this is 3 to the power of m I will take. So, this is 10 is there already. So, 21.6 divided by 2.4, 21.6 divided by 2.4 is equal to 3 to the power of m. So, I think 24 if I take 6 was a 24, 4s if I take 5, 6, 7, 8, 21.6 means roughly how much it is going to take, 10s is 240, so 9s I can take, 9s are 36, 3, 18, 9, 21, so 9s I will take. So, this is nothing but I can take this as 2.4 1s are 2.4 point, decimal is cancelled, anyhow it is 9, okay. So, this is going to be 9 is equal to, that is 9 is equal to 3 to the power of m. So, this step is going to become 3 square is equal to 3 to the power of m. So, 3 gets cancelled. So, m is equal to 2. So, keep this m is equal to 2 standby, take this m is equal to 2 standby. Now, keep working out between first and second is over. Now work out with the second and third. First and second is done. Now go for second and third experiment. So if you're going for second and third experiment, so here this is going to be, keep that data as it is, because we need to compare. If you're comparing, then go with 3 divided by 2, because you're finding that 4.32 into 10 to the power of minus 3 is higher than 2.16 into 10 to the power of minus 3, because powers are same. So therefore 3 divided by 2 experiment. 3 is 4.32 into 4.32 into 10 to the power of minus 3 divided by 2.16 into 10 to the power of minus 3 is equal to, here the concentration of nitric oxide is same, but the concentration of chlorine is getting doubled. So therefore first we will take, because anyhow M value already we got. So here 0.03 divided by 0.03 to the whole to the power of M into 0.04 divided by 0.02, because the concentration is getting doubled. So this term I am cancelling, because anyhow the value is same, the concentration is same. So this is 10 to the power of 3, 10 to the power of minus 3, and 10 to the power of minus 3 also gets cancelled. I think this is 2 times. So if this is 2 times, this is going to become 2 to the power of 1 is equal to, this decimal is same, so this is 2 to the power of n. So 2 gets cancelled, n is equal to 1. So n is equal to 1 and m is equal to 2. So n is equal to 1, m is equal to means m reflects the second order. So therefore again final expression, rate is equal to K into concentration of nitric oxide. Actually m represents 2. So nitric oxide order is second order, and chlorine concentration is n, which reflects 1. So therefore overall order is 2 plus 1, that is 3, that is third order reaction. So we have to search for the option now. The option is third option, which has third order reaction. So therefore third order is the correct answer for the given tabular form, the experimental evidence from the table. From the table we have calculated the order of reaction, but not looking at the stoichiometry of the equation. Though the stoichiometry of the equation is 3 here, what you need to understand is, in the entrance examination sometimes if your luck favors you, 2 moles, 1 mole, third order reaction, your bit option gets correct. But sometimes every time our luck need not favor, because order of reaction never depends upon the stoichiometry of the equation. In this particular question, because the molar coefficients are 2 and 1 and the final order of the reaction also it is 3, sometimes without any with fluke guess, if you try to guess, definitely it may be third order, but the third order actually you are supposed to calculate like this, taking all the experimental data in 2 different combinations, first 2 combinations and next 2 combinations, 1 and 2 in one case and 2 and 3 in another case. Then upon solving you will get the overall order of the reaction as third order reaction. So my dear students, I would like to give you one last shortcut in chemical kinetics. There is one formula which 14th one. Suppose if a problem is given to you in such a way that a reactant, 1 gram of reactant A, which is giving rise to products at time t is equal to 0, it is 1 gram. At time t is equal to t, initially when time t is equal to 0, 1 gram, no amount of products have been formed, 1 gram, or you can take 1 mole per liter, it depends. So okay, I am taking, because it is a reactant is in form of concentration, I will take 1 mole per liter of the concentration. When time t is equal to 0, products are 0, but at a lapse of time t is equal to t, certain amount of products have been formed. So you find that you are finding that 1 by 16th amount of the reactant, 1 by 16 moles per liter of the reactant is left. So 15 by 16 is the amount of products which has been formed. So based on this, that means 15 by 16 moles per liter of the products have been formed. So the remaining concentration of 1 mole per liter is 1 by 16 is the remaining concentration. So now suppose the half life, the total number of half lives involved, the half life for converting from 1 gram, when 1 gram to 1 by 16 mole per liter is changing to, when 1 mole per liter of the concentration is changing to 1 by 16 mole per liter of the concentration, let the half life be T half is equal to 30 minutes, obeys first order reaction. obeying the first order reaction. So, I am giving you one shortcut method. W is equal to W by W naught is equal to 1 by 2 to the power of n. So, what is the total time? Now, from this observation, what is the total time? Total amount of time taken to convert to 1 by 16th of initial concentration is what the question is being asked. The initial concentration is what the question is being asked. So, that is the case. Then we already knew that this 1 by 16 is nothing but remaining amount of concentration after the lapse of time. W is nothing but remaining amount of concentration. W is 1 by 16, W naught is 1 mole per liter, 1 mole per liter, this is 1 by 16th mole per liter. Okay. So, this n represents here number of half lives. N represents the number of half lives. Number of half lives is given by the formula n is equal to T by T half. This is the formula which you need to understand. So, now what I am going to do here is number of half lives also we should know, or else you can directly take W is 1 by 16 means, that is if W is 1 by 16 means 1 by 16 into 1 by 1 is equal to 1 by T to the power of number of half lives is T by T half. So, what I will do here is T by T half already we know it is 30 minutes. 30 minutes I am going to take. So, 1 by 16 is equal to 1 by T to the power of T by 30. So, 1 by 2 to the power of 4, because 2 cube is 8, 2 to the power of 4 is 16. So, this is going to become equal to 1 by 2 to the power of T by 30. So, this is nothing but this step you can take it as 2 to the power of 4 is equal to 2 to the power of T by 30. So, 2 gets cancelled. So, 4 by 1 is equal to T by 30. So, T is equal to 120 minutes is the exact amount of time which is required for converting 1 mole per liter of the initial concentration to 1 by 16th mole per liter of the concentration. If it wants to remain means exactly 120 minutes we need, that means total number of half lives are 4, that means 1 to half to 4, 1 by 4 sorry, 1 by 4, 1 by 4 to 1 by 8, 1 by 8 to 1 by 16. So, 1, 2, 3, 4 half lives, number of half lives are 4. So, n is equal to 4, without taking the formula also you can calculate. Number of half lives are 4, number of half lives are 4, number of half lives are 4. So, here 30 minutes, here 30 minutes, here 30 minutes, 30 minutes and here also 30 minutes. So, total it comes to 30 plus 30 plus 30 plus 30, total 120 minutes is required for converting 1 mole per liter of the initial concentration to remain to 1 by 16 concentration of the reactant is present. So, this is one shortcut method where we can calculate the numericals based on the number of half lives.